So this is our second session at looking at electrons and bonding beyond A level. We're going to look at the 4 quantum numbers that describe an electron in an atom. I'm largely going to deal in this session just with going through the information, and then I'll do a follow-up video with lots of examples, but it might be in between those two that actually you want to have a go at trying to apply the understanding of the 4 quantum numbers to what you already know about the structure of an atom in terms of the fine structure, the SPDF structure, etc. So the thing that we need to know about our 4 quantum numbers is that every electron in an atom is described by a unique set of quantum numbers. And that links into what we've already learned, which is the Pauli exclusion principle. So the Pauli exclusion principle, which largely explains why electrons actually go into orbitals spin opposed, so with opposite spins, states that it's impossible for an electron to have 4 or an identical set of quantum numbers. So they can, the first 3 can be the same, but then when we get to the very last one, they've got to be different. So we've already seen one of our first quantum numbers, and we've used it probably quite a lot in our studies so far, but haven't called it this, which is n. And that's the principal quantum number. That's related basically to the shell number. These are all quantized numbers, so they can have positive, negative integers, or the neutral integer of 0. But in the case of the principal quantum number, the only values it can have are integers greater than 0. So it can't have an integer of 0 or negative integers 1, 2, 3, etc. We then come to our second quantum number. So each electron is going to be first described by its principal quantum number. Then once we've described that electron by its principal quantum number, we describe it by its value of L, which is its orbital angular momentum. This word links in to the wave function in the Schrödinger equation, which describes the shape of the orbitals, but that's way beyond the purview of what we're looking at the moment. We simply need to know that. The possible values of L are actually the same as the possible values of N, except for the fact that whereas N, the principal quantum number, could only have integers greater than 0, L can have values as integers of greater than and including 0. So 0, 1, 2, 3, etc. And because it has this value of 0, the possible values are linked to the principal quantum number. So the possible values are of L are equal to n minus 1. But the fact that L, unlike n, can have a value of 0 means that actually it's the same number. So for example, if we were looking at the principal quantum number of 3 or the third shell, then the possible values of L are going to be 0, 1 and 2. So once we've done that, we then come to the ml value. So once we've described our electron by its principal quantum number n and then its orbital angular momentum, we then describe it by its magnetic quantum number, which is ml. So m with a subscript lowercase l, magnetic quantum number. And these are determined by the maximum value of L. So it's possible to have any values from minus L, so we can say magnetic quantum number can have any value from minus L in integers including 0 up to plus L. So integer intervals including 0. So, and I am going to do an example here for us. So for an example, if L was equal to 3, then the possible values of ML are minus 3, minus 2, minus 1, 0, 1, 2 and 3. So there are 7 possible values for ML if we have a orbital angular momentum of 3. So before we get to our last quantum number, let's just review what we've looked at. So we've got n as our principal quantum number, that's the shell number. That's basically the maximum distance an electron can be found away from the nucleus. So a principal quantum number of 1 describes the maximum distance it's possible to find an electron. The orbital angular momentum is related to the shape of the orbital. And the magnetic quantum number are all going to be degenerate numbers, so they're all going to have the same energy for a particular value of L. So where we saw ML here, all of these values will have the same energy, they are degenerate. We come to our very, very last quantum number, and that's M with a small lowercase s, and that's the magnetic spin. Now magnetic spin can have a value of +0.5 or -0.5. That doesn't describe the charge, it simply describes the quantum number as being +0.5 or -0.5. So I'm not going to go over any examples here, that will be in a follow-up video. What we really need to have away from this particular session, and the thing that you're going to need to learn from this session, are what these 4 values, these 4 symbols mean. So n is the principal quantum number, L is the orbital angular momentum, ML is the magnetic quantum number, and MS is the magnetic spin. We need to know that the principal quantum number is basically the shell number and can have positive integer values greater than, and obviously not including, 0. So 1, 2, 3 and so on and so on. So that's quite an important idea there. That the possible values of L, the orbital angular momentum, are described by n-1, but it is possible for the value of L to be 0 as well. So effectively the possible values of L are equal to the principal quantum number when you take into account the fact that 0 is a possible value. The magnetic quantum number is determined by the value of L, and we take the maximum value of L in its negative sense, and we go up in intervals by integer intervals including 0 all the way up to the maximum positive value of L. And then the final quantum number is the magnetic spin, which can have just a value of +0.5 or -0.5, and that hopefully we'll start to see later explains how electrons are found spin opposed, or so with opposite pins. Thank you very much.